Very short talk, and the goals for this would be to have some questions leave in your mind, maybe saying, are we doing machine learning? Why aren't we doing machine learning? Or what are some of the barriers? So this is, we could do a full day on this. We could do many full days on this. This is really just to tee up some questions and maybe make some provocative statements that we can have some healthy debate in the lunchroom in the exhibit hall. Don't need to talk about the patient journey. I put this in every single presentation that I do, and I've done it for over a year now. We've all had personal experience, unfortunately, with diseases, be they family members or ourselves. And this is a diagram they give nurses at the University of British Columbia in Vancouver, Canada. And really, from a patient journey perspective, we know that what we're really trying to do is understand, number one. Number two, quantify, easier said than done. And hopefully influence clinical practice. So when you're a solution provider like us, we definitely want to help you along your journey to understand the patient journey. So first provocative topic of the day that I'll only spend 30 seconds on, and then we'll move on. Well, what is statistical prediction versus machine learning? The comment I'll make about statistical prediction, those of us trained in inferential statistics, is that really inferential statistics is based on the assumption that you're able to find some reasonably good model that could have generated the underlying data. And you're going to have these slides, so I won't read the other bullet points to you. Machine learning is really about what is the best algorithm to answer my question? What are some good predictive methods that I can try and sort of experiment with? That's a little bit different posture than inferential statistics. Now, being a recovering frequentist statistician, I was very enamored by the data scientists and machine learning folks and computer scientists of the world a number of years ago, and I said, well, what are you doing that I can't do? And really what they're more willing to do than I was willing to do was to experiment with things. And what we're going to go through is a really brief experiment of trying out some different machine learning algorithms on a very simple data set and just kind of ask ourselves a question, isn't this something that I could do? Knowing that your data is probably way more complex than this public data set I have. I'm using the Wisconsin breast cancer data set. It's really small, 700 observations, 10 variables. You think, wow, is that ever a small data set? But it's actually been used in a lot of data mining competitions, which is why it's kind of neat, because you can kind of compare what you do to what data mining competition winners have done with this data set. And our goal here is just to find an algorithm that achieves 95% plus accuracy, a really lofty goal, you would think. And our recipe is really what we're going to do is we're going to acknowledge this recipe, and you're welcome to peruse this in the slides or talk about it with me after. We're going to skip ahead. We're going to make the strong assumption that your data is in order. We're going to make the strong assumption that you've done transformations and you basically figured out the data such that now you're ready to just run some algorithms. So I know 80% of the time is spent on data, 20% on the fun stuff. But we're going to skip to the 20% of the fun stuff. So let's pretend we have a nice, large, hopefully, data set, and we're going to run through just testing out some algorithms. The toolbox. The toolbox for this analysis, which I'm happy to say I did myself, was RStudio using R. So we use R, open source language, tons of great stuff out there, both in the blogosphere, in terms of how to use these machine learning algorithms, and of course all of that is open source. So we use RStudio to sort of develop, test, break, fix, iterate through some algorithms. RStudio is a good program. I saw Shiny up on one of the slides. You can use that. And then Spotfire and Tear. So this is now getting closer to the
Revity signals
sphere of influence. Spotfire, as you know, is a visualization tool, but did you also know that it's got an enterprise runtime R engine in it, which runs on average 10 to 100 times faster than open source R. So what you can do, and what I've done, is I've built a little analysis in RStudio, and then I've started the process of creating a machine learning app. Not completed it yet as of today, but essentially what I want to be able to do is go in and show a little app, and I know app scares us technology vendors, like don't say app, everyone's got apps. But it's really just a dashboard with some options to run these machine learning algorithms, a little bit more point and click. Now we don't want people running off into the Wild West. I know statisticians and data scientists alike are like, step away from the algorithm and call your data scientist. Do not touch the keyboard. But I'm trying to just say that I think we should make it a little bit more approachable, that we can have a conversation with our data science teams if you're not particularly interested in doing these things yourselves. So as I said, let's get to the fun stuff. Ran 7 machine learning algorithms on our little training data set. Remember, Machine Learning 101 splits your data into some reasonable set of training and validation. But what a lot of people may not understand is that you should also cross-validate within your training data set so that when I prepare a graph like this for accuracy of my 7 algorithms, that those are based on actually 10 runs within. So it basically creates a mini validation within the training set. So that's a pretty key distinction, a tip for those that may not use this stuff very often. And then you can see we've got really good accuracy on 6 of our 7 methods. The methods, just in case you're wondering, are k-nearest neighbors, a regularized generalized linear model, a straight-up logistic regression, naive Bayes, linear discriminant analysis, support vector machines, and decision trees. You're like, oh my god, that's too many. But, you know, why did I pick those 7? I don't know, experience. But the point of the story is you can do a lot of testing of these algorithms pretty easily these days. So then we say, well, maybe one singular model is not the best, maybe a group of methods. And so there's this whole area of machine learning called ensembling. The simplest example of an ensemble is a linear combination. What's a great example of a linear combination? The mean. Right? So you could take, in theory, you could take a very simple mean of a bunch of model parameter outputs and call that a basic ensemble. But of course, a lot of the algorithms are a lot more complicated than that. In my ensembles, I've tried a random forest, a stochastic gradient booster, a cart 5.0, and bagged trees. So if you notice, I've blasted through 11 methods here in about 2 minutes. You notice there's no Greek symbols. There's no, why did you use this one? Why did you use that one? And the reason why I'm not going into that is, number one, I don't have time because lunch is waiting for us on the other side of the wall. And number 2 is, I think, from my perspective as a data scientist, it's okay to kind of have a loose understanding of kind of what these things are doing just to get you in the front door of machine learning. I'd rather you go try it and not really understand the mathematics of a stochastic gradient booster, rather than say, well, I'm not doing that because I don't even understand the title or the name, and I don't understand, I need to take a Coursera course on machine learning before I can even touch this stuff. When we ask ourselves, are we ready for machine learning? I would say anyone who's willing to learn about it is ready. And so, in this case, for this example, ensembling is probably overkill. You know, we probably don't need to use ensembling because it's a very simple data set. It turns out that when we run the k-nearest neighbors, which is a very, very simple and often dismissed algorithm now in modern machine learning technologies. However, the very simple k-nearest neighbors did a really good job, 99%. You go, wow, really, is that accurate? Well, don't forget we're running it on a small sample size. But just to demonstrate concepts, we've run through, in less than 5 minutes, an entire machine learning project. Now you say, well, what's all the code? You wrote all the code, you had to go learn about stuff. It doesn't take long to do these things, honestly. And if you have something like Spotfire or RStudio or Shiny or something, you can get started with a small data set and running these things really quickly. And like I say, there's lots of great information out there on the web on this topic. So 3 tips, I'm getting close to the end. 3 tips for machine learning projects: follow a process. Gave that little diagram, you're happy to show that to you and explain it. A process, that's to me, as a practicing data scientist, machine learning is really about a process. And if you follow a process, then your decisions become ones about which algorithms to use or which various decisions I want to make, and less about like getting lost in all the different things you can do. I mentioned cross-validation when you're training algorithms. I think it's really, really important. As a matter of fact, it's a best practice. So don't forget k-fold cross-validation. I use 10-fold, you can use 5. There's different people have different opinions on how many folds to cross-validate with. And don't forget your 80-20 split for final prediction. So when we go to a production model, we still want to have a holdout sample to test the final algorithm on. And try ensembles. Learn about ensembles. Pretty cool technologies and algorithms they have in there. You know, the people that predict the hurricanes use them. So when you see them on the Weather Channel or on the local news, and they say, well, I've even heard them say, well, the ensemble model has the hurricane going this way, which in North Carolina we're very concerned about ensemble models because the ensemble can say it's coming our way. It's just a real world example of ensemble models being used to predict hurricanes. So I thought that was pretty neat. And so, final slide, are we ready for machine learning? I think, you know, I've been at this conference all 4 years, and I've seen the content grow to include more of these types of talks. When we did the first one, we were talking about, well, someday we should do machine learning, but we're not there yet. And the guys from Berg always do a great job of giving us a really cool machine learning or advanced analytical topic every year. So I think we are. I've seen this show grow a lot in terms of the content. And you know, if you have R and Spotfire, a lot of you have our software. You can do this stuff right out of the software you already own. But we struggle with the data. It's on our roadmap. We're not there yet. I hear it all the time, and I totally agree that, you know, getting the data in a place where you can use it and all your IT initiatives are great. All I'm saying is there's a lot of teams out there using it today. Why not give it a try? Why not set up a small project that you can do off to the side while you're building up the bigger infrastructure? The technology exists. The information is there. I think machine learning is far more accessible than it's ever been in recent years. Now, caveat, this is the statistician in me talking now. Machine learning or statistical prediction is not, never, no way, a substitute for proper experimental design and or sample selection. So if you give these algorithms poorly selected or biased data, then you're going to get the exact same thing out the other side, probably biased results and things you're not happy with. So let's always remember that while, you know, the wild west of open exploration of data is here, we really do need, when we're going to make claims about our compounds, or we're going to publish a poster, or we're going to do these things, and you guys all know it's preaching to the choir, proper experimental design is critical. Thank you for listening, and please enjoy your lunch. I'll be in the exhibitor hall for the rest of the afternoon if you have any questions, if you want to debate the topic at hand. But are we ready for machine learning? I'm going to say yes. Okay.